Okay, so first thing, am I audible properly? No reverberation? Cool. So let's start with the session 2. Don't worry about the notes. I will share you all the notes. Don't worry about the derivation. You can derive it on your own later. Understand the process here. What do you do here? What you have to do is just understand what I'm trying to why am I deriving all these things? What am I trying to explain? Just understand that. Don't worry about the derivations and other things. We can obviously discuss about the derivations and all those things in the doubt discussion group. For now, your motive should in the session should be just get the very fundamental ideas of why am I doing it. You can take a notebook and sit, just try to understand. If someone asks you a question maybe 10 years later, you should know that why are you doing all these things. Understand this. So starting with the today's session number 2, we'll be talking about the in today's second session we'll be talking about the performance parameters. We will be talking a little bit on the thrust equation, and we'll be talking about the performance parameters. Why are they important? Which performance parameter to use when, etc. Starting with the rocket thrust equation. F thrust equals to m dot v exit plus ae into p minus pa. There is a derivation for this where you have to take a control volume. Actually, I would like to give this as homework. Derive. See, derivations are not very important until unless you want to go into research. For practical application like numbers. Ois Raj, yourself. Thank you very much.
Sorry.
No issues. So let's continue. F thrust equals F thrust is basically the force rocket engine is providing. Is the equation says is equals to the total mass flow rate from the rocket nozzle. This is the nozzle. M dot is basically how much masses of the gases. See, there are gases going outside. So how much mass of the gases are going every second outside the nozzle? Units kg per second. SI units. I will follow SI units always. And VE is the exhaust velocity. Now let me explain you about this part. This is a rocket nozzle like this. This is the engine. This is the nozzle, and this is where the nozzle ends. So if I map it, this region will be something like this. If you observe from the front view. Now this area, this is the exit area or the cross section area at the exit. Now here, when the gases are exiting, it has some velocity that is called as the exhaust velocity or the exit velocity. Okay, then this is the convective thrust or momentum thrust generated due to the change in momentum of the gases. Next, there is another part of thrust which you cannot ignore, and basis of which we design the rocket nozzles: pressure thrust. So the overall thrust of the rocket engine consists of two parts, that is momentum thrust and the pressure thrust. It is dependent on the change in the pressure. So PA is the ambient pressure. Oh, actually I have written it. Why am I writing it twice? I will just, yeah. So PA is the, here you can see, is the ambient pressure or whatever pressure the surrounding is. For example, if you are on the sea, standing on the sea, then sea level ambient pressure is 1 bar or 1 atmosphere. But if you are in the space, deep space, then there is the pressure is almost 0 bar, no pressure, 0 bar. So that is called the ambient pressure. It can be anything, but not necessarily your PE. Subscript E means exit, A means ambient. Not necessarily your exit pressure will also be equal to the ambient pressure. It can be different, and most of the time it is different. When it is equal, then it is called as optimal condition, and when it is different, then you have a pressure thrust also that is affecting your rocket in a negative way. Let me tell you, it is Here you can see it is a plus, but it is actually affecting in a negative way. So that is the main concept. Your thrust is maximum when your exit equals to ambient pressure. The next thing is the mass flow rate. M dot consists of two terms, that is mass flow rate of oxidizer plus mass flow rate of fuel. Because I already mentioned you that rocket engine consists of two mass flow, two things, something which can burn fuel, something which can support burning oxidizer, both of them together called as a propellant. So M dot is the M dot, or I can write M dot P here, mass flow rate of propellant. Now you can the thrust equation you can also write as thrust equals to m dot into ISP, basically reducing the number of equations, number of terms. Why I told you that ISP is a performance parameter, now you will come to know that thrust is equals to m dot ISP, that is ISP is the specific impulse. Now most of the people thinks that ISP has unit seconds because everywhere they see seconds. I mean the SI unit basically, but no. We will derive the unit of ISP. So let's solve the misconception. Thrust is newtons, or newtons can be written as kg meter per second square if I'm not wrong, and then equals to kg per second into ISP. So kg cancel, second cancel, ISP as meter per second. ISP has a unit of velocity, that is why ISP is also called as overall exhaust velocity. Note it down because it's not written in my notes. ISP is also called as overall exhaust velocity. If you read NASA SV 125, there you will get it. By the way, it's a documentation. NASA SV 125. Now, why do we write ISP in seconds? Now, let me tell you. So, if you go around the world, humans are stupid. We have several units like FPS, CGS, etc., etc. And because of which, if ISP is the most important parameter, if the ISP has a variation in units, then your whole equations, everything will go wrong, and your performance calculations, everything will go wrong. And this problem of units have actually happened in the actual engines. That is why we divide the ISP value with the gravitational constant acceleration of the Earth, that is g. If ISP is in some other unit, G will also be in some other units. Now let's see what we get. ISP unit is meter per second. I'm doing an SI as of now. Gravity is meter per second square. Meter cancel, second cancel, unit is seconds. Wherever you go in the world, in this stupid human world, everywhere you will find the unit of times as same in seconds. That is why ISP is most of the time internationally written in seconds, so that there is no confusion going around. Cool. I hope this is clear. I will undo whatever I did. Yeah. Now, I will explain you the. I have already explained you the meaning of IS definition of ISP when it is written in meter per second. That is, it is the overall exhaust velocity. As you can see here in this equation, F equals to m dot. If you take common from the above equation of thrust here, if you take the m dot as common, then you have a very big term over here that is called overall exhaust velocity. This is the velocity and this is another part of velocity. If you check the unit, this will also be having the unit of velocity and ISP, hence it is called as overall exhaust velocity. I will just undo whatever I did. Cool. Now, definition of ISP when it is written in seconds. Very simple thing. A bike has a mileage, a rocket has a ISP. Let's talk about the analogy now. ISP is basically you have 1 kg of fuel. I'm telling you the definition in seconds. You have 1 kg of fuel. You have to produce 1 Newton of thrust. You know 1 Newton is like 100 grams force. 100 grams force or 100 grams weight you can say. When you have to produce 1 Newton of thrust force for with the help of 1 kg propellant, for how much time that 1 kg propellant can produce 1 newton of thrust is basically the ISP in seconds. So when the propellant has more energy, it can produce more thrust with I mean, it can produce 1 newton of thrust for a longer time. And if it has low energy, then it can produce 1 newton of thrust for a shorter time. That is the definition of ISP in seconds. Cool. Typical value of ISP is 200 to 465 seconds for a chemical propulsion system. Highest is 465 seconds for KVD1 engines. KVD1 Russian engine, of which the cryogenic upper stage of India is a copy of. So congratulations, India has all liquid engines as a copy of something. And developing, that's why we are developing on our own as of now. Talking about ISP, it is the overall performance parameter. When you want to compare two different rocket engines, you take the parameter ISP. But ISP consists of two terms, that is C star and CF. I will explain you. Just understand what these terms are. Derivations and everything you can do on yourself, believe me. Any course can teach you derivations, not the fundamentals. It depends on the interaction between the learner and the instructor. So ISP has two terms. One is C star, also known as characteristic velocity, and another is CF, also known as thrust coefficient. Let's see. This rocket engine you can see here is divided in two parts. One is the combustion chamber where energy is produced. One is the nozzle where energy is where energy is converted from one form to another. That is from thermal to kinetic in terms of chemical propulsion system. Chemical thermal propulsion system. So I told you the rocket has two parts. Rocket engine has two parts. One part is where energy is produced. One part is where energy is converted. So that is why overall performance ISP should also be divided in two parts. One part which says how much energy is produced, another part which says how much energy is converted. Because not necessarily your all produced energy can be converted into kinetic energy or in other form. Then your efficiency will be 100%, not possible. Even the Carnot cycle has efficiency of 60 something, 66. So yeah, the part where energy is produced is called as combustion, which happens in the combustion chamber here. The part where energy is converted is called as nozzle, which happens here. There is a specialty of the rocket nozzle throat. What is a rocket nozzle throat now? So rocket nozzle throat is the smallest section in the rocket nozzle. It's called as a throat. Basically, you have a neck, you have a throat. Your throat is basically the smallest section of your neck. Similar way, for the rocket nozzle also the smallest area is called as a throat. Now, whatever is happening behind the throat is not getting affected by whatever is happening outside the throat. This is the best part of the rocket engine. If the flow is choked, means choked flow means the Mach number or the velocity of gases at the throat is equal to the velocity of speed of sound, because below and after the speed of sound a lot of things changes. So that is why before the whatever is happening before the throat cannot be affected by whatever is happening out downstream or later than throat. Okay, now I will be using two terms, upstream and downstream. You have a stream coming in this direction. Whatever is, I take a particular section, whatever is opposite to the stream is upstream, whatever is uh, with the whatever direction is with the stream is downstream. So whenever I say upstream and downstream, please understand. So combustion is happening, and you and for measuring the parameter of combustion, that how good the combustion is, you have C star or the characteristic velocity. I will tell you why it is called characteristic velocity and not anything else. And then you have a nozzle where you have thrust generating. So there has to be some thrust coefficient that scales up. That is the energy conversion factor. That is the thrust coefficient. Now you have combustion happening. There is high temperature and the molecular products had some molecular weight or weight. Yeah, molecular weight. At the end of the day, you have to accelerate the gases to higher velocity. So how much you can accelerate or how much maximum velocity you can accelerate your gaseous combustion products is the characteristic velocity. The definition I've written on the screen: how much energy your propellant releases when burnt, or basically to what velocity. I mean, it's the same thing. To what maximum velocity you can accelerate your combustion gases to is called the characteristic velocity. I mean, if you take all the energy from it without any nozzle or something. Now, let's understand this characteristic velocity in a very simple way. People think that if your combustion has higher temperature, then it is better. But no, there are two terms. Characteristic velocity means how much you can accelerate your gases to, how much velocity. Now, if you have gases which has higher molecular weight and you have same amount of energy, and you have another gases which has lower molecular weight, then we all know inertia. Lower weight substances needs low energy to go to same velocity. Or if you gain same velocity, for example, you have a cycle, you have a train, you try to push your cycle, you try to push a train maybe you can't push, but cycle you can push because of the law of inertia. Same thing is applied to the molecules also. If you have molecules with lower molecular weight and higher temperature, then your C star will be higher, means you can accelerate your gases to higher velocity. So C star or characteristic velocity is directly proportional to under root of T by molecular weight. T is the temperature, M is the molecular weight of product. Okay, choking, mark number 1 at the throat. Mark number is basically velocity of gas divided by speed of sound. A is the speed of sound. Now I told you what an ISP is. Now, sorry, what a C star is. To maximize C star, we should have highest temperature and lower molecular weight. So whenever you do NASA CE analysis in the upcoming session, I mean next part, after 10 minutes, I will be explaining you what is NASA CA. What you should target is maximize the C star and not maximize the temperature. This is a misconception. So if you want to become a good rocket propulsion engineer, that is why I am focusing on this point multiple times. You have to maximize the temperature, minimize the molecular weight of the products. So I will tell you how actually we will be doing this. In today's session only we will be doing all these things. So it will be very interesting, fun. Yes, Aryan.
So I've got a question now. The propulsion work that my friends and I do here, we kind of like to think about C star as the efficiency of the combustion process itself, and we tend to think of it as to how the exhaust would basically perform if we had no nozzle. Is that like a good way to think about it? Like if we remove the nozzle entirely and just consider the combustion chamber, is it a good way to analogize the,
Yeah, I got your
let's
question.
say
I
the,
got your question.
yeah.
So I will explain you. So this is a hypothetical case. It's like if you have if your combustion is going on, you have the thermal energy stored, and when you convert all the thermal energy and give it to the gases in the form of kinetic energy, your gases will be accelerated to some velocity without any nozzle. Yes, without any nozzle, actually. Your gases, all the thermal energy is given to gases. Gases are in space, vacuum, and the gases are accelerated to a maximum velocity that is called the characteristic velocity. So, your way of thinking is actually perfect.
Cool. All right. Thanks.
So, yes, very good question, a good answer, and let's understand the next term, that is the CF, or the thrust coefficient. So actually, I will explain you about the converging diverging nozzle, and you will auto and okay. Let me tell you about the thrust coefficient now. One is the parameter of the chamber, another is the parameter of the nozzle. So depending on your nozzle design, how good is your nozzle design, your CF or the thrust coefficient is affected, and hence your ISP is affected. For now, only understand this much. We later will be talking about thrust coefficient in detail later in the course. Let's do one more small thing, or understand why do we have converging diverging nozzle. I In the previous session I explained you about the converging diverging nozzle. Now let me explain you why do we have a converging diverging nozzle. Because you can say, sir, when you're telling that the area is decreasing and your velocity is increasing, then why are you increasing the area again? That is where the concept of speed of sound comes into the role. Whenever talking about gases, rocket engines, the only thing that changes the behavior of gases is the speed of sound. Very important, speed of sound. Let's start with the rocket nozzle, a converging diverging nozzle. Let's understand why do we have a converging diverging nozzle in the rocket nozzle and not only a converging. First thing I want you to derive on your own is area velocity relation. Basic gas dynamics may be simple for some, may be difficult for some. Don't worry, it's a basic gas dynamic stuff. This is called as area velocity relation, because based on which we will be doing the whole thing now. I have drawn a rocket nozzle here. This is the combustion chamber. Actually, I changed the color of the pen. Green. I prefer blue. I don't know if we have blue color here. Okay, something like that is there. Okay, so in the combustion chamber, combustion chamber is a pressurized thing. So it's like a house, a room where you are fitting 200 students. A small room where only one person can sleep, and you are fitting 200 students. Do you think can any student move? No, right? No student can move. So the velocity of every student becomes zero. Similar is a combustion chamber, where in a small space you are combusting the gases, giving gases very high energy, but it cannot move because the space is less. So the temperature increases, because in a room when a lot of people are there, there is thermal conductivity and the temperature increases. I'm just giving you the analogy, don't take it seriously. So similar way here, a small volume giving energy, the temperature increases, pressure increases, but the velocity cannot increase in the combustion chamber. Velocity is zero, and Mach number equals to velocity of gas divided by velocity of sound. Velocity of gas is zero, Mach number also zero. So Mach number is zero here. And if you see the area velocity relation, u is the local speed of gas, du is the change in speed, dA is the change in area, a is the local area, m is the Mach number. Now let's understand when the Mach number is less than 1, because you see the variations are across the Mach number 1. When the Mach number is less than 1, then this particular term will be negative, correct? Because anything less than 1 square minus 1 is negative term. Now area is always a positive term, you cannot make it negative. Change in area, if this term is negative and you're decreasing the area as we are doing in the nozzle, then dA is also negative, correct? And this negative term multiplied by another negative term becomes positive. So du by u equals to dA by a. dA is negative. This I have told this as a constant, m square minus 1. It is negative. Negative into negative is a positive term, and u velocity is basically always positive in this case. So that is why your change in velocity du is positive. It means that when your Mach number is less than Mach number 1, or less than the speed of sound, then you have to decrease the area to increase the velocity. Now let's see another thing. This concept, anyone has any doubt here, please ask now. Just understand the concept. Cool. So you have, according to area velocity relation, if you have subsonic gas. Okay, Mach number less than 1, subsonic. Mach number equal to 1, sonic. Mach number greater than 1, supersonic. You can write it down. Again, I will tell Mach number less than 1, subsonic. Mach number equal to 1, sonic. Mach number greater than 1, supersonic. Mach number greater than 5, hypersonic in the Earth atmosphere. That number can be varied when if you are going in some other atmosphere. So now let's talk about the velocity, what is happening after the throat. Before that, let me explain you a very small term, that is speed of sound in the gaseous medium. U is the local speed of sound. You take this region, you take this region, you take this region, you take this region, you take this region. Every region will have a different speed of gases. Sorry, U is the speed of gases. So every region will have a different speed of gases. That is the U. That is the local speed of gas at a particular cut. So if you take a cut over here and you see there is gases here has some speed, that is called as the local speed. Talking about the speed of sound in the gaseous medium, equation is A equals to under root of gamma RT. Gamma is Cp by Cv, specific heat ratio. Cp is specific heat constant, specific heat at C is specific heat of gas at constant pressure. Cv is specific heat of gas at constant volume. Gamma is the ratio of both, and it is a very important dimensionless number in the domain of rocket propulsion. R is the gas constant, is universal gas constant divided by molecular weight of the gases. T is the temperature. So what happens after Mach number? Okay, okay, this is not okay. Fine. What happens after the throat? So you see, you are decreasing the area, Mach number is increasing because velocity is increasing. Mach number increasing, velocity increasing because speed of sound remains same. Speed of sound is not changing. Again, decreasing the area, Mach number increasing. At the throat, Mach number is 1. Always. At the throat, Mach number is 1. After the throat, Mach number is slightly greater than 1. And now let's see the area velocity relation again. When Mach number is greater than 1, this term becomes positive. And now if you area is always positive, if you decrease the area, then this term will be negative. And then your velocity will, U is positive, so negative into positive, it will be negative. So your velocity will decrease. So that is why after the throat, if you have area increasing, your dA is positive, that is change in area. Basically, after the throat, this is the case. If you take dA is area final minus area initial. This is the area final, this is area initial. Your final area is more than the initial area. That is why dA is positive, and that is why m square minus 1 is also positive here. I mean, it is positive, dA is positive, u and a are positive, so du, that is change in velocity, is also positive. This is the reason why after throat your velocity, your area increases and not decreases. Everything on area velocity relation, homework is to do there. Look at the basic rocket nozzle below the before throat, Mach number less than 1, velocity increases as area decreases. At throat, Mach number 1. After throat, Mach number greater than 1. Mach number is velocity of gas upon speed of sound. At after throat, Mach number greater than 1, and area increases, Mach number increases. Now question is, someone asked me this in the previous session, so I will just explain you. If you have a supersonic gas coming from here, you are decreasing the area, then Mach number will decrease. At the throat, Mach number will be 1, and after the throat, Mach number will be again decreasing further. This is, then it will be no longer a nozzle, then it will be called a diffuser. So it has application, it will be called a diffuser after that. Cool. Now, a small part, choke flow. Choke flow is choke flow. I explained you already. Mark number one at the throat is choke flow. A choke flow is only a function of upstream condition and is independent of downstream condition. Very important. Take a screenshot, note it down, do whatever you want. Next session, I mean the upcoming session after the break, this will be very important. So, okay, what does it means? It means that when your flow is choked, whatever is happening over here cannot affect the combustion chamber. It means that the C star. Before here, C star. After here, CF, ISP. It means that when you are firing your rocket engine in the space, when you are firing in the water, when you are firing in lava, when you are firing on sea, when you are firing on land, the combustion chamber performance will not change wherever you fire the engine. Doesn't matter until and unless the flow is choked. Until and unless the flow is choked, your performance, combustion chamber performance will not change. What wherever you fire. That is why C star is separate and CF is separate. And this is very important in the upcoming. I mean, the third part of the session. I will be explaining you about this. Okay, so here the lecture ends, but here the lecture ends finally.